All right. Hello, everyone. In this video, we're going to be talking about normal subgroups and quotients of groups. So we're just going to jump right in. If H is a subgroup of G, H is said to be normal if XH X inverse equals H for all X in G. And notice this is equivalent to saying XH equals HX. And so notice, like in the last video on cosets, all the things we dealt with multiplying by an element on the left. And here we're saying that it has to be the same if we multiply on the right. Now, this does not mean that XH equals HX for all X in G and H, little h in H. It means if X is in G and H is in H, then XH X inverse is also in H, right? It doesn't have to be the same little h, it can be something else. Okay. Of course, if G is abelian or a commutative group, then all subgroups are normal. We denote H is a normal subgroup of G as H and then this sort of triangle operator and then G. And so this is actually standard notation, unlike my subgroup notation. This is actually standard notation. I've seen it in multiple places. Okay, so the first theorem we're going to prove about normal subgroups is actually kind of a surprising result. And it says that H is a normal subgroup of G if and only if H is equal to the kernel of some group homomorphism with G as the domain. Right? And it doesn't matter what this output group is. All that matters is that I have some group homomorphism with G as the domain. Okay. So we're going to prove the backwards direction. So we're going to start with if H equals ker F, and we're just going to show, right, that H satisfies the normality condition. So let X be in G and H in H, then F of X, H, X inverse is equal to F of X, f of h, f of x inverse. Now h is the kernel of f, so f of h is the identity element. Which means we can drop it from this product, and then I have f of x times f of x inverse, which is also equal to the identity element. And so x inverse is in the kernel of f, which is equal to h. Okay, so that direction is actually very simple. The other direction is trickier, though, because we have to show that this normality condition allows us to we have to find some group homomorphism. And what we're going to do is construct what is known as a canonical homomorphism. It's sort of the, it's like the homomorphism that you associate with having a kernel of H. And so, notice that if I multiply two cosets, then I have A, H, B, H. Now, if we are using the fact that H is normal now, right? So HB, I can swap that around now. I can't normally do that, right? But now I can because of the normality condition. The normality condition says that I can always swap around a multiplication like that. Now HH is just H. And so I've multiplied two cosets and I've gotten another coset back. Thus, we have a multiplication on the set of cosets. And this is going to be actually a group operation. So the first step is showing that this product is associative. I'm going to skip that step because it really just boils down to the associativity of the product, like the associativity of G itself. The identity is the coset corresponding to the identity element, which is just H, and inverses the inverse of the coset AH is just the coset of A inverse. Okay. Now let f be a function from G to this, now what we know as a group, this quotient, and this is going to be called a quotient group. And the way we're going to define this function is we're going to send a group element to the coset of that element. Then f of AB is equal to ABH, which we know we've already computed is the same thing as AHBH, which is f of A, f of B. So f is a homomorphism. The kernel of f consists of x and g such that f of x is the identity, right? The identity is the is just the coset corresponding to h, right? So this means that xh equals h. And this is the same thing as the set of x and g, such that x is an h, which is just a fancy way of saying that this is equal to h. Right, so maybe let's elaborate on why this should be the case. Clearly, clearly we have that H is a subset of the kernel because any element of H is going to satisfy this equation, right? We've already showed that in the previous video. So this is from last video. And then if x h equals h, then how should I say this? X h and right, we have to have just some, we can pick some equality, x h equals h prime, and then we can write x as this product of elements, and these elements are in H, so this is an element of H. And so this shows that the kernel of F is a subset of H. Therefore, since we have H as a subset of kernel of F, and kernel of F is a subset of H, we have that they are equal. Okay. And so this shows us, right, what we were trying to prove is that H is normal if and only if H is a kernel. And so if we're given that H is normal, we can construct this, well, first of all, the set of cosets becomes a group called the quotient group of G by H. And then we can construct a homomorphism from G to that quotient group with a kernel of H. Now, the next thing we're going to do is show the first isomorphism theorem. Sometimes they have enumeration, sometimes they don't, and I'm not really sure if there's a standard enumeration. I'll have to check before I make the next video. So the next video is going to be all about isomorphism theorems. But this one just flows so naturally with the idea of quotient groups. And we have time. It's only 13 minutes in. So this theorem is going to state the following. If we're given a group homomorphism and the kernel is given to us as H, well, we just set H equal to the kernel, then G, we can define a function G from the quotient group to the image of G given by G of xh equal to f of x is a group isomorphism. So the first thing we have to prove is that this function g is what we say well-defined, right? And you have to do this a lot just sort of as a sanity check. Whenever you define something, when your domain is a set of cosets, because notice what we're doing here. XH is a coset, right? But it's not necessarily XH, right? XH is the same thing as XH, X little hh, right? So we need G of XH, which is equal to f of x, to equal G of XHH, which is f of XH. Thankfully, this is the case. So f of xh, right? F is a homomorphism, so we can break up this multiplication into f of x and f of h. H is the kernel of f, so f of h is just the identity. And so we have the desired equality. Okay. Now we have to show it's a homomorphism. So we can do that by taking a product inside. Okay, xh times yh is the same thing as xyh. So this is f of xy. F is a homomorphism, so we can break this up. And then this is going to be f of x is g of xh, and f of y is g of yh. So G is a homomorphism. Okay. The next step, right, to show that this is an isomorphism is to show it's injective and surjective. So for injective, we just have to show that the kernel is trivial. So let x be in kernel of G. So f of x, I should say this is xh. The quotient, or the coset xh is in the kernel of G. So G of xh, which equals f of x, is the identity. Then x is in the kernel of f, which is the same thing as h. So xh equals h. Thus, G is just equal to, is the trivial subgroup of the quotient space, right? It just contains the identity coset. And thus, G is injective, right? Remember that we proved for homomorphisms, injectivity is the same as the kernel being trivial. Now to show that it is surjective, let y be in f of G, then y equals f of x for some x and G, and thus y equals G of xh. Thus, G is surjective. So we've proven that G is a homomorphism, it's injective and it's surjective. So thus, G is a isomorphism. And what was the isomorphism? It was G mod H isomorphic to f of G. So this is the first isomorphism theorem. It says that if you take a group and a normal subgroup, then the quotient group is isomorphic to the image of G under the canonical homomorphism, right? Another way of saying it is that for any group homomorphism, G mod out the kernel F is isomorphic to the image, which is a pretty astounding result. And it's one of the sort of key ideas in group theory. So that's it for this video, and in the next video we will cover more of these isomorphism theorems.